Okay, so hello and welcome everyone to week 7 of interactive live sessions for the course on Computational Fluid Mechanics for Incompressible Flows offered by NPTEL. The course is being instructed by Professor Amaresh Dalal from the Department of Mechanical Engineering in IIT Guwahati. My name is Debjit. I am a PhD scholar at IIT Madras, and like every other week, we shall be solving some tutorial problems together. So, the topic of discussion of week 7 was von Neumann stability analysis, and we saw the stability analysis of different schemes used for different kinds of equations, parabolic equations, hyperbolic equations, and so on. And in the end, we looked at the modified equations and how artificial viscosity and other higher order terms might creep in to the modified equation and then lead to numerical diffusion. Okay, so without further ado, let's start with the questions. So this is question number 1 of today's session, which is asking us which of these are ways to analyze the stability of a numerical scheme. Then there are four options given. So the four options are the discrete perturbation stability analysis, option B, the matrix method stability analysis, option C, the von Neumann stability analysis, and option D, all of the above. Now, read the question carefully first and then try to figure out the correct answer from the options given below. And once you've figured out the correct option, you can either unmute and answer or you can type in the chat box. So, this is question number 1 of today's session, which is asking us which of these are ways to analyze the stability of a numerical scheme. Is it option A, the discrete perturbation stability analysis, option B, the matrix method stability analysis, option C, the von Neumann stability analysis, or option D, all of the above? Let's have a look at the solution. The solution is indeed all of the above. So the thing is, all the three options given from A to C are different ways of analyzing stability of any given numerical scheme. They might be applicable in different cases. Uh, so the discrete perturbation stability analysis, the matrix method stability analysis, as well as the one we actually studied, that is the von Neumann stability analysis, all three of them are different techniques used to analyze the stability of any numerical scheme. Alright, so let's move on to the next question of today's session. So we will move on to question 2, which is what is von Neumann stability analysis also known as? So there is a second name for von Neumann stability analysis. Is it option A, Lorentz stability analysis? Is it option B, Fourier stability analysis? Is it option C, linear stability analysis? Or is it option D, all of the above? What is von Neumann stability analysis also known as? Is it option A, Lorentz stability analysis, option B, Fourier stability analysis, option C, linear stability analysis, or option D, all of the above? What is von Neumann stability analysis also known as? Is it option A, Lorentz stability analysis, option B, Fourier stability analysis, option C, linear stability analysis, or option D, all of the above? Let's have a look at the solution. The solution is option B, Fourier stability analysis, and there is a reason behind it. That is because what is it that we do in von Neumann stability analysis? So what we do is we consider an error term, which is the uh, difference between the actual solution and the uh, let's say if D is the exact solution of the FDE and N is the numerical solution. So the difference between them, that is the error. And this error, which is a function of both space and time, is actually expanded in its Fourier series. M is equal to 1 to N. So, this is the time coefficient and multiplied by the exponent of you know, I k m x. Is it negative or positive? Let me check once. Yeah, positive. So what we do in von Neumann stability analysis is we expand out the errors in their Fourier series, and then we say that since the original equation is a linear equation, okay, so this is one of the first things. So this type of analysis is applicable for linear PDEs with periodic boundary conditions. Okay, so this part is important here. So since the original equations are linear, we can say that each term of this Fourier series uh, are actually solutions to the original PD, and therefore we do not have to look at each different term of this Fourier series alone. We can look at any one term and then conclude on the stability of the system based on the growth factor. So this time coefficient actually takes the form of some e to the power at. So if a is positive, then that means this term would blow up as time increases, right? So if a is positive, then the this term, this am versus t, this would go something like this. It would exponentially increase if a is positive. And on the other hand, if a is less than 0, then the error would gradually decrease with time. Actually, it would exponentially decrease. So if this is for a greater than 0, let me take a different thing. So if a is less than 0, then it would exponentially decrease, and that would lead to a stable solution. And if the rest of the criteria, that is um, the rest of the criteria other than stability, that is if it is consistent as well as then if it's consistent and stable, then it would lead to convergence, right? So then we will have a convergent solution. So as far as stability is concerned, we can analyze the stability through these steps. And since the error is expanded into its Fourier series. Therefore, this technique is also known as the Fourier stability analysis. Right? Okay. So moving on, we'll move on to question number 3 of today's session, which is asking us what are the minimum and maximum wavelengths of errors appearing in von Neumann stability analysis. This is for a case with n number of grid points and delta x as the uniform grid spacing. So the spatial domain can be thought of like this. So this uniform spacing is delta, and there are total, 1, 2, dot, dot, dot. There are n number of grid points in the mesh. So, if we perform von Neumann stability analysis on this, what would be the minimum and maximum wavelengths of errors appearing in that? So, there are 4 options given below. Option 1 is delta x and n delta x. So, these are respectively. So, the first one is the minimum and the second one is the maximum. Okay. So, is it delta x and n delta x? Option A. Option B, pi by delta x and pi by n delta x. Option C, delta x by pi and n delta x by pi. Or is it option D, 2 delta x and n delta x? So read the question carefully first. What are the minimum and maximum wavelengths of errors appearing in the von Neumann stability analysis with n grid points and delta x as the uniform grid spacing? So let's have a look at the solution. The solution is very simple. Option D, 2 delta x and n delta x. So let's have a, so 2 delta x is the minimum wavelength, or I'll write it as L, not lambda, not to be confused later because we are using lambda as the Courant number as well. Right. So what happens is, let's say if we take a grid like this, sorry, so let's say this is the one-dimensional mesh in our system. So what could be the minimum wavelength? So in order to have, you know, one wave like this, we need at least 3 points, and basically there would be two spacings in between those 2 points. So the minimum one would go something like this. Right? So this is the shortest wavelength possible, and this is delta x. This is also delta x. So the wavelength of this, that is L min, would be 2 delta x, and the longest wavelength possible would cover this entire domain. So it would be something like this. Right? So this would pass through a point, not like this. Sorry. Right, and this would cover all the points. So the L min, L max, that is the maximum wavelength, that would be n into delta x. Now remember, in the Fourier series expansion, there the form of those equations were, some at of the terms. Let's say the mth term would be am t into exponential of ikmx. Sorry, this km is known as the wave number, and any km is equal to pi divided by 2 pi divided by the wavelength of the mth wave. So if you're talking about wave numbers, and then the minimum wave number that would correspond to the maximum wavelength. So the minimum wave number that would correspond to the maximum wavelength, that is n delta x. And similarly, the maximum wave number that would correspond to the minimum wavelength, and that would be 2 delta x. So 2 would cancel out, this would be pi by delta x. Alright, so there is an important distinction to be made here. In the question, wavelengths were asked and not wave numbers, so not to be confused with them. Okay. So we will moving on to question number 4 of today's session. Arrange the steps of von Neumann stability analysis in correct order. So different steps of the von Neumann stability analysis are given, but in a jumbled up order. You have to figure out the correct order and then pick whatever option given below corresponds to that correct order. So the different steps given are: step 1, check whether amplification factor is less than 1. Step 2 is determine amplification factor or growth rate. So those are two names of the same thing. Step 3 is expand the error in its Fourier series. And step 4 is write the error expression from the finite different equation. So arrange these different steps in the correct order in which von Neumann stability analysis is performed. Okay, so let's have a look at the solution. The solution is option B, 4321. Let's have a look. So first of all, what is the first step? So what we do is we have a finite difference equation to begin with, and then we put in the error terms uh, in that equation, and then okay, so more in a more detailed way, if I say so, what we do is we have the FDE in terms of n, which is the numerical solution, and the equation to begin with must uh, must be satisfied by the exact solution of those FDs as well, which is D. So we get these two equations and then take a difference between them, and then we finally obtain the FDE in terms of the error terms. The error terms are nothing but D minus N, right? So from here we get the error expression. So that is the first step, this one. Then in the second step, we uh, expand out the error in the Fourier series and take only one term, one representative term, and we do that under the assumption that the behavior of that one term would reflect on the behavior of the other terms as well, and the behavior of the error as a whole would be correctly represented by that one term from the Fourier series only. So expansion is the second step. So we started with 4, Then 3 was our second step. And then we simplify that equation to find out the growth rate, which is known as G, that is given by error at the n plus 1th term by the error at the nth time step, and error of the n plus 1th time step over the error at the nth time step. So that gives us how the amplitude of the error is progressing with time, evolving with time. So this also comes out to be some a to the power, sorry, e to the power a delta t, where if a is positive, then this term is greater than 1 and it grows with time, right? So this would be the this would be the third step, which is step 2 in the options given. And in the final step, we check that whether this amplification factor is greater than 1 or less than 1. So we take the modulus of it, the absolute value of the amplification factor, and that should be less than equal to 1. So our correct order of steps would be 4, 3, 2, 1, which is given by this option B. So option B indeed is the correct solution. Right? Okay, so let's move on. We'll move on to question number 5 of today's session, which is asking us what is the stability criterion for beta scheme for parabolic equations. If you remember the beta scheme, which was the superposition of one explicit part and one implicit part, and different for different values of beta, different combinations were available. So for the condition that beta is lying between 0 and half, so beta greater than 0 but less than half, then what is the stability criterion for the beta scheme applicable for parabolic equations? Is it option A, gamma x less than 1 over 2 into 1 minus 2 beta? Is it option B, gamma x less than 1 over 1 minus 2 beta? Is it option C, gamma x less than 1 over 2 into 1 minus beta? And or is it option D, gamma x less than 1 over 2 into 1 plus 2 beta? Read the question carefully and then try to figure out the correct option. Right. So let's have a look at the solution. The solution is option A, that is gamma x less than 1 over 2 into 1 minus 2 beta. So from the von Neumann stability of the beta scheme, if we do, then for beta greater than half to 1, it turns out that it is unconditionally stable. half beta equal to half corresponding to the Crank-Nicholson scheme, and beta equal to 1 representing an implicit scheme. Now, in this range, when beta is greater than 0 but less than half, then in this range it is conditionally stable. With beta equal to half still representing Crank-Nicholson, and beta equal to 0 is basically an explicit scheme. Now, within this region, as it turns out, gamma x into 1 by 2 beta is less than half is the stability criterion. Now, with a little bit of algebra, not much, just we will send out this term on the right hand side, and then we will get gamma x less than 1 over 2 into 1 minus 2 beta, this being the stability criterion for beta scheme to be stable, right? So we will move on to the next question of today's session. We'll move on to question number 6, which is asking us what is the expression for artificial viscosity in first order upwind scheme for first order wave equation, where lambda is a Courant number. So the artificial viscosity is given by alpha, as seen in the options given below. So you have to find out the expression for alpha as it appears in first order upwind scheme for first order wave equation. So if we do this, what is the expression for artificial viscosity? Is it option A, alpha equal to C delta x by 2 into lambda? Is it option B, alpha equal to C delta x by 2 into lambda into 1 minus lambda? Is it option C, lambda equal to C into delta x by 2 into 1 plus lambda? Or is it option D, alpha equal to C delta x by 2 into 1 minus lambda? So let's have a look at the solution. The solution is option D, that is alpha equal to C delta x by 2 into 1 minus delta 1 minus lambda. So as it turns out, so the first order wave equation is given by dou phi dou t equal to minus C dou phi dou x, right? Now, if we first discretize this and then put in the Taylor series of each equation within that, we will get the modified equation as seen in the fourth lecture of week 7. Now, how does this modified equation look like? Here we again have these the terms from the original equation, and then we have one second order derivative of spatial derivative of phi, plus there are some other terms also. So we also have, let's say, one third order term, which is let's say we represent it by alpha prime. Now, that doesn't matter over here. We are worried about the artificial viscosity only. So this value of alpha, and as it turns out, the value of alpha is equal to c delta x by 2 into 1 minus lambda. So that's why option D would be the correct answer. Okay. And here lambda is the Courant number given by C delta x, sorry, C delta t by delta x. Yeah. Okay. So let's move on. We'll move on to question number 7 of today's session. So where does artificial viscosity originate from? Does it originate from option A, the round off error, option B, the truncation error, or option C, the discretization error? Where does it actually originate from? Hello. हाँ, चेन्नई है. আচ্ছা আচ্ছা হ্যাঁ ওই একজনের নাম্বার ছিল কিন্তু সে এখন ছেড়ে দিয়েছে. তুই একটু প্রত্যয়ের সাথে কথা বল, ওর কাছে কোম্পানির নাম্বার আছে তো ওরা অন্য গাড়ি দিয়ে দেবে. হুম, ঠিক. So let's have a look at the solution. The solution is option C, discretization error. So let me explain it this way. So round off error, first of all, does not really contribute here because we can see from the equations itself the artificial viscosity arises. Round off error would uh, appear in the you know during solution in a computer itself with some finite precision. So round off error couldn't be the origin of artificial viscosity. Now, truncation error is also not the origin of artificial viscosity because we are eliminating truncation error in going from PD to FD itself and not worrying about it later. So where do we get the modified equation? So in the FD itself, if we put back the Taylor series and then we see that that is not going back to the original PD. So it is actually the difference between the original PD and the discretized version of it. The difference between these two, not exactly sum, but you know a mathematical difference between these two is actually the origin of artificial viscosity. So that's why discretization error, in a sense, is the origin of artificial viscosity. Is that clear? Okay. So we will move on. We will move on to question number 8 of today's session, which is asking us what is the effect of numerical viscosity on the solution? Not really effect. I should write down here effects. It could have multiple effects. Is it option A, numerical dispersion, option B, numerical dissipation, option C, both A and B, that is both dispersion as well as dissipation, or option D, none of the above, that is none of these are effects of artificial viscosity? So let's have a look at the solution. Solution is option B, numerical dissipation only. So as we saw, let's say if the solution, the original solution would have been like this, then due to numerical dissipation, the numerical solution that we obtain would be dispersed a little bit like this, would be dissipated a bit like this. So it would spread out. Instead of a sharp gap, it would spread out. So that spread is basically caused by effects called diffusion in fluid flow. The momentum diffusivity is actually viscosity. So here there is no physical viscosity in the physics of the problem, but due to the uh, errors which we introduce, one of those being the artificial viscosity, we can see uh, a diffusion of the solution in this way, and this is known as dissipation. So this is the effect of artificial viscosity on the solution of the problem. Okay, so let's move on. We'll move on to question number 9 of today's session, which is asking us match the following in relation to numerical effects in modified equation. So this is a match the following type of question. We have two columns with two options each. You have to pick out the correct combination, which term corresponds to which term. So these are in relation to modified equations. So the left hand column has two options, option A even terms and option B odd terms, and in the right hand column we have again two options, option 1 dissipation and option 2 dispersion. So basically what is being asked here is there are higher order terms. These can be divided into even terms and odd terms, basically the order of them. So if let's say there is dou n phi dou xn. If n is even, then that term we will call even, and if n is odd, we will call that term to be odd, right? So which of them causes what effect? So does even term cause dissipation or dispersion? So that would determine A equal to 1 or A 2. Similarly, odd term would do the other thing. So you have to pick out the term with its effect. And once you figure out the correct combination, you can select it from the options given below. There are two very simple options given here. So is it A1, B2 or is it A2, B1? Pretty simple, right? Okay, so let's have a look at the solution. The solution is A1, B2, that is all the even terms cause dissipation and the odd terms cause dispersion. So in the modified equation, all the higher order terms which are even, they are responsible for dissipation in the solution, and all the odd terms, they are responsible for dispersion in the solution. Okay. So we will move on. We'll move on to the last question of today's session. So here also we were talking about numerical effects of the modified equation. So earlier we saw which terms cause dissipation and dispersion. Now we will see what are the effects of them. So the uh, column on the left hand side has two options. Option A smearing and option B wiggles. So what is which of these are caused by dissipation or dispersion? That way you have to match now. So does dissipation cause smearing or wiggles? Does dispersion cause smearing or wiggles in the solution? That you have to figure out, and then you can uh, select the correct option from select the correct solution from the options given below. Once again, we have those two very simple combinations, A1 B2 or A2 B1. So let's have a look at the solution. It is A1, B2. That is smearing causes dissipation. Sorry, the other way around. So dissipation causes smearing and dispersion causes wiggles. So smearing is something that we already saw. So if we have an original solution like this, the numerical solution that we get gets smeared out like this. So a very sharp uh, jump we had. So that gradient is smeared out over a certain distance. So it was very sharp drop over here. Instead, we got something which extends over some length. So it's getting smeared out. So this is known as smearing. And what are wiggles? So if we again had a similar exact solution like this, we do not get that. We get something like this. So these are what are known as wiggles, and these are caused by dispersion, which are in turn caused by odd terms, higher order odd terms in the modified equations. I hope that makes things clear. So that was the last question of today's session. So thank you all for joining, and we will meet again next week. Thank you.